of a function and a closed interval. The derivative of ax is 800 minus 4x. If we set it to 0, we find x equals 200. We follow the algorithm for finding the maximum of a function on a closed interval. Endpoints are 0 and 400, and critical number is 200. If we find the values related to 0, 200, and 400, we see the maximum of the area is 80,000 when x is 200. This means the maximum area of the farm is 80,000 meters squared, and the dimension of the field is 200 meters by 400 meters. Example 2. We have a piece of sheet metal, 60 by 30. We cut 4 equal squares from 4 corners, and by folding up, we make an open top box. We are looking for the value of x, the length of the square that we cut from the corners, to have the maximum volume. If we use this diagram by folding the white parts up, we have this box. The dimension of the box is x, the height. The length is 60 minus 2x, 60, and we cut 2x from 2 corners, and the width is 30 minus 2x, with the same reasoning. 30 minus 2x. Therefore, the volume is x times 60 minus 2x times 30 minus 2x. Obviously, x is greater or equal than 0 and is smaller or equal than 15. 30 divided by 2, 15. The volume is x times 60 minus 2x times 3 minus 2x, which is 4x3 minus 180x2 plus 1800x. And x is between 0 and 15. We find the derivative, set the derivative to 0. The derivative is 12x2 minus 360x plus 1800. If we set it to 0, x is either 23.7 or 6.3. 23.7 is indivisible, therefore x is 6.3. V at 6.3 is 5196. And V at 0 is 0, V at 15 is also 0. This means 5,196 is the maximum volume when x is 6.3. By plugging 6.3 for x in the dimensions 60 minus 2x and 30 minus 2x, we find the width and the length of the box. Our last example, Jan and Ada are both training for a marathon. Jan's house is 20 kilometers north of Ada's house. At 9 a.m. on one Sunday, Jan leaves his house and jogs south at 8 kilometers per hour. At the same time, Ada leaves her house and jogs east at 6 kilometers per hour. When are Jan and Ada closest together, given that they both run for 2.5 hours? A simple diagram is here. Jan's house, Ada's house. AI is 20 kilometers, and moving south, and Ada moving east. After T hours, AN is at J and Ada is at B. AB is 60 and IJ is 8T. Notice that the distance is speed times time. This means JB can be written as a function of time. By using Pythagorean theorem in triangle ABJ, ST is square root of JA to the power of 2 plus AB to the power of 2. JA is 20 minus 80, and AB is 62. It can be simplified as 100T2 minus 320T plus 400. We find the derivative of this function using power rule for derivative. Derivative is the exponent times the function to the power of exponent minus 1. 1 over 2 minus 1 is negative 1 over 2, times the derivative of the function times the derivative of 100T2 minus 320T plus 400, which can be simplified as 100T minus 160 divided by square root of 100T2 minus 320 plus 400. T is greater or equal than 0 and smaller or equal than 2.5. The critical numbers is 1.6 by setting derivative to 0. We find the corresponding values to 0, 1.6 and 2.5, and we see after 1.6 hours their distance is 12 kilometers, which is minimum. This means at 10:36 a.m. they are closest to each other. In summary, in an optimization problem, we must determine maximum or minimum value of a quantity. An optimization problem can be solved using a mathematical model that is developed using information given in the problem. The numerical situation represents the extreme value of the model. One important part of the calculus is optimization. We have an algorithm for solving optimization problems. Step 1, understand the problem, identify the quantities that may vary, determine the function in one variable in this course that represents the quantity to be optimized. Draw a diagram, label the diagram, determine the domain of the function to be optimized using the information given in the problem. Use the algorithm for finding maximum, minimum, absolute maximum, minimum of a function on a closed interval. Answer the question. To understand optimization, next session we solve question 8 on page 145, question 14 on page 146, and question 15 on page 147. Thanks for watching.